Thank you. Can you hear me? No? I don't know how to do this with mics. I'll just hold it. Okay, yeah, and so this is joint work with my collaborators at Northeastern, Dustin and Amal, who are around here. Okay, so yeah. So the goal for this in this work was to design a language incorporating gradual typing and parametric polymorphism while satisfying what we could call the fundamental theorems of each language feature. So for gradual typing, that's this property I like to call graduality, or also known as the dynamic gradual guarantee. And then for parametric polymorphism, that's obviously Reynolds relational parametricity. And as Jeremy just mentioned, this might sound very familiar if you were at POPL last year, where this paper decided this question and said, parametricity is, like non-interference, incompatible with the dynamic gradual guarantee. And so I don't agree with this. So what I want to talk about is, what graduality and parametricity are, what the sort of real incompatibility that I think they ran into here is, and then how we can circumvent that incompatibility to make a language that satisfies both graduality and parametricity. Okay, so let's just review what those properties are. So as we saw in the previous talk, gradual typing is about migrating from more dynamically typed programming style to a more statically typed programming style gradually over time. And graduality says, oh, okay, well, if all I did was change the types in my program, then I'd like for there to be a sort of predictable effect on the program's behavior. And specifically, it says that the static program's behavior refines the behavior of the original dynamic program, but it possibly has additional runtime checks due to having stricter types. And so more formally, it says, if we started with a dynamically typed program, we added some annotations to it, then either this more statically typed program runs to a type error, in which case maybe the dynamic one does or it doesn't, or they have equivalent behavior. They both terminate, they both diverge, or yeah. Okay, and so this graduality property really captures the intuition we have about gradual types, which is that the type is a kind of enforceable property about programs, and more precise types result in stricter type checking. Okay. Now to parametricity, universal types classify functions that work uniformly across different representations, and parametricity for them gives us things like free theorems. So for example, here we have the identity function, and a free theorem for the identity function type in language with effects is that if I call a function that has the type of the identity function on a value, it can only possibly output the input that it was given. Okay, and for parametricity, we're also interested in existential types, which model abstract data types, and they give an interface similar to module systems. So, for instance, here's an existential type for sets of integers, where there's an abstract type S, that's the implementation of our sets of integers, and then we get three operations here: empty set, inserting into the set, and checking for membership. And then parametricity for existential types is all about data abstraction. And so the idea is with existential types, we might start with a simple list-based implementation, but then later on we might replace it with a tree-based implementation. And parametricity allows us to reason that this doesn't change the behavior of the program overall. And so it gives us a principle that if we can show that this list-based implementation is related to this tree-based implementation in a certain way, then plugging them into a larger program has the same behavior. Okay. So there's actually kind of similarities between these two properties, right? So they both give this kind of syntactic to semantic, local to global principle. So with gradual typing, adding types results in only adding errors. With parametricity, swapping out small modules will result in not changing the behavior of the program. And mathematically, we also get similarity. They're both proven using logical relations that have a similar structure. Okay. Okay, so that's what they have in common, but now let's look at what this supposed conflict is between the two. So let's look at previous work on gradual polymorphism. So first of all, there's the kind of straw man approach, but this is really just like the obvious approach. Just take what we know about gradual typing and apply it to system F. And what happens is you don't get the same kind of parametric reasoning. So for instance here, we have a type for all XX to bool, And in system F, it's a free theorem that since we can't really inspect this x, we shouldn't be able to use it to determine what the output is, so this should have to be a constant function. But the problem is with gradual typing, of course, we can essentially cast between any two types by using the dynamic type. So here I am ascribing the dynamic type to x, and then I'm ascribing the type Boolean, essentially casting the input to x. And what happens is, if we just have a simple substitution-based semantics, I'll apply this to a Boolean, and then this will be a cast of a Boolean to the type Boolean, which succeeds. So instead of getting a constant function, we got a identity function. And so parametricity doesn't hold at all for these systems. And so no data abstraction whatsoever. So the naive approach, it'll give us graduality just naturally, but the parametricity theorem doesn't hold. And then, okay, so the community's looking at this and they say, okay, what can we do? Maybe we can enforce the parametric reasoning at runtime. And this idea goes back to Morris, 1973, and it's called dynamic sealing. And the idea is for each abstract type in the program, we're going to dynamically create a pair, a seal and unseal pair, where seal packages up values and puts them into an opaque box. And the only way to actually get the value out is with an unseal function. And then the idea is that we're going to seal any abstract values flowing out into the world where it's unknown. And then when it's flowing back into the module, we'll unseal these values. And this has been the approach of several papers in the literature to try to recover parametricity. And the idea is to combine is to take system F in the same syntax as the naive one, but now try to automatically insert these seals to get the free theorems back. Okay, so let's look at how that works. So here is that same problematic function from the naive case, but now we'll reduce it with a type-directed approach to sealing. So first we add a store of seals that we're generating them freshly at runtime. And when we reduce the type application, we generate a new seal first, sigma of type bool, and then we're going, because the input type of the function is the abstract type, we're going to seal the input and make it opaque. And then what happens is we reduce again to a cast, but this time we're casting a sealed Boolean value to the type Boolean, which is not the same as a Boolean, and so this this cast will instead fail. So this free theorem at least is safe. Okay, but on the other hand, the graduality theorem is in jeopardy. So here's two programs, and the one on the right has type for all x dyn arrow x, and the one on the left is an identity function, and the only difference between the two is what the type of the input here is, right? So the one on the left is the result of making the types in the one on the right more precise, right? So we should have this graduality principle that the one on the left should error more. But if we run it, the one on the left here, it has this annotation of x, and it just runs as an identity function. So we take a step, and because the input type is abstract, we're going to seal the input. And then because the output type is abstract, we'll also unseal the output. And then this reduces to unsealing a sealed value, which returns the value, just like an identity function. On the other hand, on the more dynamically typed side, there's a question, you know, are we going to seal the input, which has now dynamic type? And what these systems say is they say, well, the dynamic type is not an abstract type, and so I won't seal this input. But then, when I reduce, I'm going to now be unsealing a value that's a Boolean and not sealed, and so that'll result in an error. And so this violates the graduality principle, and basically what happened is we took a program that was more dynamically typed, and we added type structure to it, and it removed what you could think of as a dynamic type check from the program. And so that really doesn't conform with our expectations of what a gradual type system does. Okay, and the problem really here was this ambiguity when it comes to dynamic type. You know, if we're using the types to determine whether values are sealed or unsealed, then the dynamic type, it's ambiguous which one it should be. And if we pick either one, then there will be a violation of graduality. So there's no global choice to determine this. And so the real incompatibility that I think they were running into was that graduality is incompatible with this type-directed approach to dynamic sealing. Okay. And so then if we look back at how they actually proved their claim that parametricity was incompatible with dynamic gradual guarantee, we can see the flaw in their proof. So basically what they did was they said, okay, we'll prove that graduality is false within this language based on the logical relation that they use to formalize parametricity. And the problem is that this is the logical relation that they used, which was based on prior work, to be fair. It's not a standard parametricity logical relation. It's kind of a specialized logical relation for gradual parametricity. And we know that it's not standard parametricity because we found a violation of parametricity in their calculus, which you can see the paper together. So we can't really say that parametricity and the dynamic gradual guarantee are what are in conflict here. Instead, it's this type-directed notion of sealing. And so back to our table, we see that this type-directed notion of sealing, it definitely doesn't have graduality. And then the parametricity is more in question. Some of these calculi seem to have parametricity, and they definitely protect some free theorems, but not all of them. And all of the logical relations that they use are kind of suspect because they didn't catch this violation. Okay, so now let's move forward. So we know so we can't conclude that graduality is incompatible with parametricity. Instead, we're going to say, oh, graduality is incompatible with this type-directed approach to sealing. And so our approach is we still wanted to have a calculus with sealing. And so what we're going to do instead is we're going to have the sealing be explicit in the program and see if if we can make a language that satisfies both of these principles. And so we are able to make a language that has both of these properties, but there is a caveat that we changed the syntax from system F. But I think morally this is the right thing to do because what the problem here with this middle approach was that we were kind of trying to have it both ways, like use the syntax of system F, but then give it a totally different runtime semantics. So instead, we're going to have a sensible system where the semantics lines up with the syntax. Okay, so let's look at the language that we designed, which I call PolyGv New, which has a kind of fresh polymorphism. And the idea is that this generation of seals is going to be visible to the programmer, and the use of sealing and unsealing is going to be explicitly programmed. So let's look at existential types. So first of all, here's an existential package for that integer set type in system F. And then here's the version of it in PolyGv New. Okay? So let's step through it. So first of all, instead of just writing a type for to instantiate the package, we're going to give it a name X here. And so this new type X is sort of exported from the module, but it's also defined to be used within the module. And then within the module, whenever we're exporting abstract values, we need to make sure to seal them. And then whenever abstract values are flowing in, we have to explicitly unseal them. And so this is actually quite similar to Morris's original paper, and it's also very similar to the way that new types are used in with Haskell modules to get data abstraction. Okay, so let's look at some abstract syntax. So first of all, the unpack rule is just the same as in system F, but the pack rule has changed now. So above we have a system F pack rule where we say we type check the body of the module with the type B, where we've substituted in the instantiating type X, A for X. And the difference on the second rule in PolyGv New is that instead of substituting in A for X, we're type checking M under the knowledge that X is isomorphic to A. And M can use that knowledge to seal and unseal. Okay, so we've extended the context. We have normal variables, and then we have the abstract type variables as usual in system F. But then we have this new notion of a known type variable or a type name definition. And this idea of the known type variables we borrowed from this paper, non-parametric parametricity. And the idea is that if you know that X is isomorphic to A in your context, then you get access to the seal-unseal isomorphism between A and X. Okay. Okay. And then the operational semantics. When we unpack a package, it will generate this fresh seal sigma, and then we will substitute that sigma into the body and the continuation. But note here that there's no sealing being inserted. The sealing is already written inside of M. And then, of course, if you unseal a sealed value, you'll just get the value back out because it's an isomorphism. Okay. Next, we have the universal types, and we basically design the existential types first, and then we did the universal types by a kind of duality. So at the top here, we have system F's identity function applied to a value, and then the bottom we have the way we would write that program in PolyGv. And so what we have here is, like the existential case, we give a name to the abstract type that's been instantiated, and then we use that name to seal the input to the function and unseal the output. And you might notice this rule is a little unusual because this binding structure is kind of inside out. So this name that we do in the type application is then used in the continuation of the type application. And so this is maybe not the most realistic language design, but we discussed some alternatives, such as doing an A and F restriction on this type application, but this one corresponds most directly to system F, which is why we chose it. Okay. Okay, and then, so we have to adapt that by including an extra context in the output, and then the type application sort of exports it out, and the operational semantics is pretty similar. Okay, and then how do we actually prove graduality and parametricity? Well, in the past, both of them have been proved by logical relations techniques. So in general, you might think, oh no, we might have to do two logical relations. But what we actually found is we were able to totally unify the proofs of the two properties by using a generalized relational formulation of graduality, where parametricity comes out as just the reflexivity case. So in a strong sense, like, they're more unified than they are incompatible. Okay, and so there's a lot more in the paper. There's a full operational semantics, all this stuff. And then we include some proofs of free theorems, some of which use the dynamic type and some of which don't, to show how that affects your data abstraction. And then, so for some future work, we want to see if we can use this existential calculus or adapt it to a more realistic dynamically typed module system. And I'd be curious if these fresh universals really correspond to any programming feature or not. And then finally, some of the same authors propose a similar conflict between graduality and non-interference, as we saw in the quote. And so I'd be very curious if there's a similar workaround there by changing the syntax. Okay. So final takeaways. First, graduality and type-directed computation are a tough mix. But graduality and parametricity are compatible if you're willing to change the syntax. And graduality and parametricity are really analogous properties, which comes out formally in the fact that we can prove parametricity as the reflexivity case of our graduality proof. And thank you. I'll take questions.
Maybe I'll go with the first question on Slido. It says, graduality is incompatible with type-directed sealing, quote, from you. Is that a formal claim? Do you think this might be contradicted at next year's POPL?
It's not exactly a formal claim, so maybe it will be disproven next year at PoPL. But well, I would say I think there is maybe a workaround if you use non-determinism, like if you non-deterministically decide to both seal and unseal things. But I think as a deterministic sealing strategy, it's incompatible because it seems like there's two competing demands, that dynamic type wants to be sealed and it wants to be totally revealed at the same time.
Is there hope for a nicer surface language that could be elaborated into this?
So certainly you can, I think you can already elaborate system F into this. The problem is then you run into the graduality issue. And so like in system F, you don't have to write the seals because there is no dynamic type. And so there's no ambiguity. But then once it's elaborated into something where it's explicit, then it needs to sort of remain explicit, I think. Not sure if that answers it.
So our next